So hello everyone. In this video, uh, in Thevenin and Norton theorem part, I am going to discuss today about the maximum power transfer theorem, and after that I will solve some problem related to maximum power transfer theorem and also Thevenin theorem with independent sources. Then after that I will go for Thevenin theorem with dependent sources. So what is maximum power transfer theorem that I will going to discuss. So suppose this is our circuit where I have written VTH Thevenin voltage and Thevenin resistance I have already calculated, and I have already calculated in part 1 of this video. So its description will be the description is already shared here. So in this case, suppose our load is RL and now it is connected between the terminal A and B. So this resistance is variable resistance, and what should be the value of this variable resistance so that the power transfer in this load is maximum. So that condition, if we get, that is the called maximum power transfer in the load resistance RL. So how can we get this? It is very simple to get. Let us see here. What is the value of current I? I will be simply VTH voltage divided by resistance RTH plus RL. This is the current flowing in the RTH and this RL resistance also. So now what is the power in this resistance? Power in load resistance RL is equal to PL equal to I square multiplied by load resistance RL. So what is our I? Putting this value I here. So it is VTH over RTH plus RL square multiplied by load resistance, this RL. This is our PL. We can also write this equation as it is VTH square divided by and multiplied by RL and divided by RTH plus RL square. So we have to obtain the condition for maximum power, means PL should be maximum. So as we know from the very fundamental rule of the differentiation, so power will be maximum. Power will be maximum if dPL by differentiation with RL is equal to 0. Why I am differentiating with RL? Because this resistance is variable here. This RTH is not variable, it is constant, and VTH is also here constant. So our variable is resistance is this load resistance. Meaning thereby physical meaning is that what should be the value of this resistance so that the power available in load resistance becomes maximum. So that we have to extract. So it is a very simple differentiation. We have to differentiate this with respect to load resistance. So this portion is the constant, this is variable, this is variable. So we have to differentiate it. So differentiating dPL by differentiation with respect to RL equal to, this is VTH, which is constant that I am taking outside, and using the rule of division. So in the rule of division, first we have to differentiate it, DRL by DRL multiplied by denominator RTH plus RL whole square. Again we are putting here minus sign and differentiating this denominator and multiplying by numerator. So RL here multiplied and differentiating this denominator means DRTH plus RL square divided by differentiation with respect to RL and divided by a square of denominator. Denominator is RTH plus RL whole square means power 4. So if you differentiate this is cancel out. So here we differentiate, 2 will come this side. So this differentiation, and we have to make it 0 for maximum power. So bringing this side, it will become 0. Dividing this side, it will be 0. And here RTH plus RL is common in both the side. RTH plus RL is common. So taking common. And here RTH plus RL. And here minus this differentiation, 2 will come here. And 1 already this RTH is taken common. So here our 2 RL will be here. 2 twice RL will be here, which is now what we get, just this minus will be here. This term will go this side, cancel out, and RTH minus RL will be equal to 0. This RTH minus RL equal to 0. So RTH equal to RL. It means if for maximum power transfer, the Thevenin resistance must be equal to RTH. Thevenin resistance must be equal to load resistance. If this is the condition, then our power transfer will be maximum. This is the only one condition. So now we have seen the power transfer will be maximum when the Thevenin resistance is equal to this load resistance. This is called load resistance. And this is our Thevenin resistance. And this is Thevenin voltage VTH. So to transfer maximum power, RTH must be equal to RL. Now after this condition, we have also to find out the efficiency. What will be the efficiency? So this is the condition to transfer the maximum power. Now we have to find efficiency. Efficiency means output power by input power, and output power is actually power in load resistance divided by input power. So here current flowing is I, and efficiency is written by eta, and here our current is flowing I, and here the voltage is V, and during the maximum power transfer, this RL is also equal to RTH. So my task is to find the efficiency during the maximum power transfer. Suppose power is transferred maximum here. So during this condition, what is the efficiency? So to calculate this efficiency, we have to use this relation output power by input power, and output power is nothing but it is the power in the load. So in load circuit, we have to calculate the power. So first we find the value of current. What is the value of current here? The current is VTH divided by twice RTH. Because this RL is equal to RTH, so RTH plus RTH is this much. So output power, what will be our output power? Means power in load means current square multiplied by resistance of the load, and resistance of the load is nothing but it is the Thevenin resistance. So now I am putting here the value VTH divided by twice RTH square multiplied by RTH. So it will be equal to VTH square divided by 4 RTH. Here RTH square will be there, but RTH cancel out, so 4 RTH. So PL, load power or output power relation is this. Now we also need to find input power. So power input, P in, means this voltage multiplied by this current. So this voltage is VTH multiplied by current I, and VTH is VTH. And what is the value of I? I is this much. VTH by twice RTH. So it will be equal to VTH square divided by twice RTH. Now this is input power, this is output power. So efficiency N will be equal to output power by input power. So VTH square divided by 4 RTH and divided by input power. This input is VTH square divided by twice RTH. So this VTH will be cancelled out, this RTH will be cancelled out, and 2 will go upside. So it will be 1 by 2, or if you convert in percentage, multiply by 100, so 50%. So this much efficiency is obtained during the maximum power transfer. So this much efficiency is not a good efficiency. So this is too low as efficiency for energy conversion device. Such device must have load resistance for larger than that corresponding to the condition of maximum power. However, in electronics devices, the objective is to obtain maximum power output irrespective of device efficiency, and hence condition is always used at the power stage of electronic system. Of course, the 50% power lost in the system, device and component must be suitably dissipated to limit the temperature rise. So this type of efficiency we are using only for electronic circuit because efficiency is too low. So 50% part will go in the loss. We are getting only 50% efficiency. So 50% will go as loss. And so temperature will rise. So to limit this temperature rise, we have to make some compensator to compensate the temperature rise. So this is mostly used for electronic circuit. So this is a problem from Nagarath's book, and the problem is like that. You find Thevenin equivalent viewed by resistance. Viewed by this resistance, we have to find the Thevenin resistance. The value of R for which maximum power dissipation in R, and the value of power also. So just I have seen a relation that RTH equal to RL, then power transfer is maximum. So we have to utilize this. Power transfer will be maximum. So we have to use this. Means we have first to find the RTH. So how we find RTH? It is already explained in part 1. So to find the RTH, voltage source is shorted. So voltage source, I am drawing here, voltage source is shorted and current source are open circuited. So this is the voltage source shorted. Then I am putting the resistance, and this current source is open circuited here. And this portion A and B is opened. And this is 30, this is 12, this is 4 ohm, and this is 12 ohm. So from here A to B, we have to see the equivalent resistance. So now the equivalent resistance between A and B is called Thevenin resistance. So you see, if I put current from here, current going like I1, I write just here, and I1 goes here, I2 goes here, and I3 suppose goes here. So this all current has to come here also. I should be here also equal to I1 plus I2 plus I3. See, this I1, this I2, both are in parallel, and this I1 plus I2 coming and going from this direction. I1 plus I2, none of the part will go here because this part is open circuited. So these two resistances are in parallel and its equivalent is in series with this resistance. So this parallel equivalent will be 4 multiplied by 12 divided by 4 plus 12. So it will be 16. So it will be 3. This 3 and this 12 will be in series. So 3 plus 12 in series, and this series resistance will be in parallel with this. Parallel with this 30 ohm. So 15 multiplied by 30 divided by 15 plus 30. Two resistances are in parallel, so just equivalent resistance. And this is called RTH. So this is 45, so 15, 3 is 45 and 3, 10. So its equivalent resistance will be 10 ohm. So this 10 ohm resistance we have to consider for the maximum power transfer. So in question it is asking find the value of R for which maximum power is being transferred. So for maximum power transfer, the value of R will be equal to RTH, and RTH, that is 10 ohm. Means 10 ohm resistance we need to get the maximum power. Now our again question is asking you what will be the value of that power. Also we have to calculate the power also. So to calculate the power we need to find the Thevenin voltage across A and B, and this Thevenin resistance is obtained by putting all the current and is 10 ohm. RL is how much? It is equal to also 10 ohm, and this is 12 volt. So it is 12 volt. So I have calculated the Thevenin equivalent resistance, which is equal to 10 ohm. Now our task is to find the voltage across the open terminal A and B. So let us draw the equivalent circuit to find the voltage across the terminal A and B. And going to draw the circuit, and circuit is like this. So the circuit is, this is 4 volt source, 4 volt, and the 4 ohm resistance here. Another resistance is 30 ohm. Here one resistance, that is 12 ohm. This is 12 ohm. And the voltage source I'm going to draw here by converting the current source into voltage source, so that our circuit becomes quite simple. So we have to multiply this 12 ohm by 2 volt, 2 ampere. So it will becomes 24 volt. So now point is like this, and we have to calculate the voltage. This is our open terminal A and B. We have to calculate the voltage across this 30 ohm resistance. So now let us see how can we do this. So for this we need just 2 loop. We have to consider this I1 current and this I2 current in this loop. So there is a very fundamental rule. How can you find this? Suppose this current I1 is flowing from here A, I'm going to write this C, D, E, F. So our current is flowing from 4 ohm, 20 ohm and going this here. But this branch has one common element also, and here I2 current is also flowing in this 12 ohm. So 12 ohm is common for I1 and I2. And if I go this loop, then this I2 will go upside and I1 will go downside. So just applying the Kirchhoff voltage rule, KVL. So we will write this equation very easily. So KVL will give us, so this 4 and 12. So 4 plus 12 multiplied by I1, and this I2 is common, so taking it minus 12I2, and our entering point is negative, so you write it in negative 4 volt equal to 0. So just this equation we can write 16I1 minus 12I2 equal to 4, and 4 taking common, and it will cancel each other. So we will get the value 3I1 minus, 4I1 minus 3I2 equal to 1. This is equation number 1. Similar equation we can write for this closed path. So for this closed path, I2 is going in 30 ohm, 12 ohm and 12 ohm. So again KVL for loop 2. This is loop number 1 and this is loop number 2. So 30 plus 12 plus again 12 multiplied by I2, and I1 is common for this, so we have to write minus 12I1 plus 24 equal to 0. Going entry point is plus, so we have to write plus. So this is Kvl analysis. In fact, I will share its link to the video also. You can go and see how we do Kvl analysis. So 12, and this is 12, this is 30, and then it will be 54 I2 minus 12 I1. So we can write simply minus 12 I1 plus 54 I2 equal to minus 24. This is equation number 2. So this is equation number 2. So using the equation 1 and 2, from equation 1 and 2, we get the value of, very easily we can find the value of I2, because there is a 2 equation and 2 unknowns are there. So simply we can solve equation 1 and 2 for I2, because I need the value of I2, and that I2 is coming here. By solving this I2 will be equal to minus 7 by 15. This I2 will be equal to minus 7 by 15. We can check very easily. It is not a difficult task. 2 equation, 2 unknown, you can solve. I2 is coming this. So I2 is minus 7 by 15. It means the I2 is not flowing in this direction. It is flowing in this direction. Negative sign only indicates. So VAB, voltage across AB magnitude, I'm going to write, it will be equal to how much? It will be equal to this 7 by 15 multiplied by 30 ohm resistance. So it will be 14 volt. So this is VTH. So VTH is known, and that is equal to the VAB. So now our almost we have solved whatever we needed. So now we're going to draw the final equivalent circuit, and our final equivalent circuit is like this. So our final equivalent circuit will be VTH, RTH. RTH is the 10 ohm already calculated. VTH is calculated 14 volt. And so here RAB, whatever resistance I have taken out, that is the R, and it is also equal to 10 ohm for maximum power transfer. So now we can find the value of current I, that is equal to 14 divided by 20 means 0.7 ampere. This is the current flowing here. Now power will be equal to, so power in load, or this is called maximum power, I square multiplied by R, load resistance. I is 0.7 square multiplied by R is 10. So it will be 4.9 watt. So this much power will be available in the load. So this was our problem to solve the value of Thevenin voltage and the load resistance to transfer maximum power. We will see one more problem. This problem is saying that okay, find the Thevenin equivalent across the terminal X and Y. So again, we have to find the value of RTH. So first of all, we have to find the value of RTH. So to calculate RTH, we have to open the current source. This current source is opened, and this is the resistance, and this voltage source is shorted, and this is 1 ohm, this is 5 ohm, this is 3 ohm, and here it is X and Y. So we have to see the equivalent resistance from this terminal X and Y. So these two will be in series and its equivalent will be in parallel. So RTH is very simply we can find these two are in series. So its equivalent will be 6 ohm, and this 6 ohm and 3 ohm are in parallel. So 6 multiplied by 3 divided by 6 plus 3. So how much its value will be? It is 18 divided by 9, so 2 ohm. So RTH is calculated 2 ohm. One part is completed. Now we have to find the VTH. So we have to modify this circuit. So how we can modify? Just to convert this current source into voltage source so that only one independent loop will be there. So calculation of VTH is very simply we can find. Let us see how we can do. This is 5 ohm. And if we multiply this 9 by 5, we get 45 volt. And then this is 1 ohm. And this is our plus minus 9 volt. And this resistance is 3 ohm. And this is our open terminal. Here we have to find the voltage at VXY. So here this is 1. So very simply we can say that the current will flowing because this side current will not go. So this is one terminal having 45 and all these resistances are in series. So simply we can say current flowing in this is I, and I will be equal to nothing but it is 45 potential difference, 45 minus 9, 45 minus 9 divided by 5 plus 1, 6 or 3, 9. So it is 9 and it is 36 by 9. So it will be 4 ampere. So 4 ampere current is flowing. So 4 ampere current will go from here to here. So this terminal voltage VXY now will be equal to 4 multiplied by 3. Means it will be 12 volt. And this 12 volt is nothing but it is VTH. So VTH is 12 volt. So now we can draw the equivalent circuit having Thevenin voltage 12 volt and Thevenin resistance 2 ohm. So we can draw very easily Thevenin equivalent, and that equivalent is shown here. So we can draw like this. Is here. So this is 2 ohm and this is 12 volt. So this is called Thevenin equivalent. Thevenin equivalent. Now we see one more problem based on dependent sources, when dependent sources are there. So this is one problem where dependent sources are there. So for dependent sources, the problem is with the calculation of RTH. So this RTH, the problem is to find the value of the RTH. So how we can find the value of RTH? So it is the problem only with the RTH because we cannot short these dependent sources, because shorting is not allowed for dependent sources because its current is depending on some other values, or opening of the current source is also not possible. So calculation of RTH is not possible by the early method, whatever we have studied. The voltage sources should be shorted and current source should be open. It is not like this here. So, but calculation of VTH is no problem. It will remain as same. Whatever method we are applying for VTH calculation, it will remain the same. So here this terminal we have to find the VTH, this terminal. So let us see how we will find. So draw for calculation of VTH. I am going first calculation of VTH. So calculation of VTH. Now we see how we can do the calculation of VTH. So it is very simple. Not so in this problem, see this is current source. This terminal is open. So whatever voltage is there here, that is called VTH, Thevenin voltage. So let us see what is the value of this Thevenin voltage. So you see here 3.5 I current is coming here and I current is coming here. So this is dependent source and this is a current source and its value is depending on the value of the current that is flowing through this 10 ohm resistance. That is why it is called dependent sources. So we can convert this current source into voltage source and we can find the value of this voltage across the terminal 20 ohm. So first we convert this source into the voltage source. Let's see. This is our plus minus 100 volt and this is 10 ohm and this current source is being converted into voltage source. So we get by converting this current source into voltage source. Let's see, I have converted this. So this 20 ohm and 20 multiplied by 3.5, this will be 70 I. Positive will be upside, negative will be downside. And this is our AB open terminal. And I current is flowing here. So we can write very easily the Kirchhoff voltage rule for this loop. So applying KVL, what we get? This, here I am going 10I plus 20, 10 plus 20 multiplied by I. And plus terminal is our entry point. So I am writing here plus 70I. You see, this is positive, this is negative, this is positive. And this is negative for this current. When current entering the higher potential, leaving negative, lower potential. So like this, entry point is positive, so positive 10I, entry point is positive, positive 20I, entry point is positive, positive 70I, and this is my entry point is negative, so 100 volt equal to 0. So we can find I equal to 1 ampere. 30 plus 70, 100. 100 I equal to 100. So I will be equal to 1 ampere. Now current is obtained. So we have to find the voltage at A and B open circuit voltage. Let us see what will be the open circuit voltage. VAB equal to VOC. So I told you if there is any confusion, you just make it simply a loop here and put a fictitious voltage source and then apply Kirchhoff voltage law. Direction you guys choose anyone. But here current is going in this direction, so positive will be here, negative will be here, and 20 ohm resistance is this. And how much current is going? 1 ampere. Current is going in this direction, and this is positive, negative, and this is 70 I. So this is Vx. So just applying Kirchhoff voltage rule from start here and going entering here. So Vx will be positive, and here entry point is negative, so minus 70 I, and again entry point is negative, so minus 20 I equal to 0. And how much I? I is 1 ampere. This 1 ampere current is going, so Vx will be 90 volt. So now my both the thing Vx is obtained. That Vx is nothing but it is VTH. VTH is 90 volt. VTH is simply calculated as early what we are doing. But the problem is with the calculation of the Thevenin resistance. We cannot open this position. So what we have to do for this, we have to go on a different technique. That technique is to find the RTH, we have to apply a different technique that I am going to write here. So this is here, the current is I and 10 ohm resistance, and here our current dependent source is how much, 3.5 I, and here one resistance is there, 20 ohm. So, and this portion is our open portion. So for that, what we have to do, taking different color. So this portion we have to make it short, means ISC. We have to calculate ISC, short circuit current. So this is 100 volt, and the current when it is shorted, so you see this I current will come here, it will not go here, it will directly go here, and this current also coming here, it will go in here. So ISC will be equal to, now it is I plus 3.5 I. So it is 4.5 I. So now we need to find the value of I. What is I? Because here 100 volt and here shorted, so it will be 0 volt here. So current I will be equal to 4.5 multiplied by I will be equal to 100 minus 0 divided by 10. So 10, so it will be 45 ampere. ISC is 45 ampere. And how much we have calculated? VOC. Our VOC was 90 volt. So R Thevenin will be equal to, it is nothing but it is VOC by ISC. And VOC already calculated 90 and it is 45, so it will be 2 ohm. So now RTH is calculated. So to calculate RTH, we have to calculate short circuit current. Now we can draw Thevenin equivalence like this. It's positive, negative, and here RTH is how much? 2 ohm, and VTH was 90 volt. So this is our Thevenin equivalent circuit. So in next video we will see some more example on Thevenin theorem, Thevenin equivalent. Okay.